You've probably heard that old saying about the wisdom of the crowd, right? The idea that if you ask a whole bunch of people the same question, their collective guess is usually way better than any single expert's. Well, what if I told you there's a machine learning algorithm that basically weaponizes that exact idea? Today, we are diving deep into one of the most powerful and popular models out there, the random forest.
But before we can really appreciate why a whole forest is so great, we have to ask ourselves a pretty important question. Why can relying on just one expert be, well, a huge mistake? Think about it. In machine learning, a single decision tree is kind of like that one super specialized expert. It could be brilliant, for sure, but it can also have massive blind spots. It can get so focused on the tiny, weird details of what it's seen before that it makes some really bad calls on new situations.
All right, so let's start right there. Let's really dig into the specific problems you run into when you put all your trust in that one single expert, that lone decision tree.
Okay, so here's the absolute core of the issue. A single decision tree has this nasty habit of overfitting. And what that really means is that instead of learning the actual patterns in the data, it starts memorizing all the random noise and unimportant quirks. It becomes like a student who just memorizes the answers to last year's test. It'll ace that specific test, no problem, but give it a new question, it completely falls apart. A random forest, though, is specifically designed to avoid this trap. It's built to be robust, to find the real signal in the noise, and to generalize to new problems it's never seen before.
So, if one expert is flawed, what do? It's simple, really. You don't ask just one expert, you get a whole committee of them together. You don't plant one tree, you grow a whole forest.
And that, at its heart, is all a random forest is. It's a classic example of what's called an ensemble method. Instead of building and trusting just one decision tree, we build hundreds, sometimes even thousands of them. And then we let them all work together to come up with a final prediction that's way more accurate and stable. We're literally creating our own crowd of experts.
Now, here's the secret sauce. This is the really clever part. You can't just have a crowd of clones, right? A committee where everyone thinks exactly the same way is totally useless. The real power of a random forest comes from the random part, from intentionally building a diverse team of experts.
And the algorithm does this with two really cool tricks. First step is something called bootstrap sampling. See, for every single tree it's about to build, it creates a slightly different training data set by pulling samples from the original data with replacement. That just means some data points might get picked a few times and some might not get picked at all. So right from the start, each tree is learning from a slightly different perspective. And second, there's random features. As each tree is being built, every time it has to make a decision or a split, it's only allowed to look at a small, random handful of the total features. This is brilliant. It stops one or two really strong features from dominating every single tree and forces each tree to become a specialist in different things.
You know, this whole strategy is the perfect showcase of a much bigger idea in machine learning called ensemble learning. The basic philosophy is just so powerful. You take a bunch of individual models, and they don't even have to be that strong on their own, and you combine them. The result? You get a single, final model that is just leagues better, more powerful, and more accurate than any of its individual parts could ever be.
Okay, so we've got our forest. We've built this diverse committee of hundreds of little decision tree experts. So, how do we actually get the final answer out of them? How does this committee make its decision?
Well, the way they do it is actually super simple and pretty democratic. If you're doing a classification task, trying to decide if a picture is a cat or a dog, every tree in the forest gets to cast a vote. Whichever category gets the most votes wins. Simple as that. And if you're doing a regression task, like trying to predict the price of a house, you just take the prediction from every single tree and average them all together.
Now, this whole approach is incredibly powerful, there's no doubt about it. But just like any tool in the toolbox, it's not the perfect solution for everything. So let's get a real balanced look at its biggest strengths and, of course, its weaknesses.
Okay, the strengths are huge. Random forests are known for being highly accurate. They basically solve that overfitting problem we talked about earlier. They can even handle missing values in your data pretty gracefully and can tell you which features were the most influential in making decisions. But there are trade-offs. Building and querying a whole forest of trees is naturally going to be slower and take up more memory than just one. And the biggest critique? It can be a black box. Because you're averaging the opinions of hundreds of models, it can be really tough to point to one single reason why the model made the specific prediction it did.
But even with those drawbacks, the raw predictive power of random forest has made them a go-to tool for data scientists everywhere. So where are people actually using these things to solve real problems out in the world?
Oh, they are everywhere. Trust me. In finance, banks are using them to spot fraudulent credit card transactions and to figure out who's a good candidate for a loan. In healthcare, they're being used to predict diseases based on patient data and even to estimate how someone might respond to a certain treatment. And anytime you're on a shopping site and it says, "You might also like," yeah, there's a good chance a random forest is working behind the scenes.
In the end, it all comes back to this one simple, powerful idea. This quote really nails it. Random forest reduces variance, which is just the technical way of saying it stops the model from freaking out over tiny changes in the training data. And by doing that, it prevents overfitting and builds a model that can generalize beautifully to new challenges it's never seen before.
And that really just leaves us with one final big question to think about. We've seen how this concept of a big, randomized, collaborative team is so effective at solving these really complex prediction problems. It just makes you wonder, if a crowd of random experts is this powerful,